Yeah, let us discuss about an interesting topic called chemical equilibrium. Okay, in this chemical equilibrium, actually there is a small picture we are showing here. That is equilibrium between dinitrogen tetroxide, which is colorless, and the nitrogen dioxide, which is brown in color. Gases forms favors the formation of latter as temperature increases from bottom to top. So this is the colors. If you observe, this is the color change. The model shows dinitrogen tetroxide and nitrogen dioxide molecules here. These are the molecules here. Okay, but in this chapter, what are the outlines we'll discuss is the concept of equilibrium at the equilibrium constant, writing equilibrium constant expressions, and the relationship between chemical kinetics and equilibrium. What does the equilibrium constant tell us, and factors that affect the chemical equilibrium? So here in this, we'll begin by discussing the nature of equilibrium and the difference between chemical and physical equilibrium in this session, and we'll define equilibrium constant in terms of laws of mass action. Another important thing here we get to see here is we then learn to write the equilibrium constant expressions for homogeneous and heterogeneous equilibria, and we'll see how to express the equilibrium constants for multiple equilibria. Then after next we examine the relationship between the rate constants and the equilibrium constant of reaction, and this exercise shows why equilibrium constant is constant and why it varies with the temperature. Then after we'll see that knowing the equilibrium constant enables us to predict the direction of the net reaction towards the equilibrium and to calculate the equilibrium concentrations. Then after the chapter concludes that with a direct discussion of four factors that can possibly affect the position of equilibrium, and that concentration, volume or pressure, temperature and catalyst. So we learn to use Le-Chatelier principle to predict these changes. Let us start the discussion. And this students achieve. See, you're going to see equilibrium. What is equilibrium? Equilibrium is a state in which there are no observable changes as time goes by. When a chemical reaction has reached the equilibrium state, the concentrations of reactants and products remains constant over time, and there are no visible changes in the system. However, there is much activity at the molecular level because reactant molecules continues to form product molecules, while product molecules reacts to yield reactant molecules. And this dynamic equilibrium situation is the subject of this chapter we have. So here we will discuss the different types of equilibrium reactions and the meaning of equilibrium constant and its relationship over the rate constant and the factors that can disturb a system at equilibrium. So the concept of equilibrium and the equilibrium constant. Actually, if chemical reactions proceed in only one direction generally, that most are reversible reactions. Most are reversible. At least to some extent, most of the reversible reactions are there. At the start of the reversible process, the reaction proceeds towards the formation of products. As soon as some product molecules are formed, the reverse process begins to take place, and reactant molecules are formed from product molecules. Actually, chemical equilibrium is said to be achieved when the rates of forward and reverse reactions are equal, and the concentrations of reactants and products remains constant. And that chemical equilibrium actually is a dynamic process. As such, it can be likened to movement of skiers at a busy ski resort, where the number of skiers carried up the mountain on the chairlift is equal to the number coming down the slopes. Although there is a constant transfer of skiers, the number of people at the top and the number of at the bottom of the slope do not change. So note that the chemical equilibrium actually involves different substances as reactants and products. Equilibrium between two phases of the same substance is called as physical equilibrium because the changes that occur are physical processes. An example, you have a vaporization of water in a closed container is there at a given temperature is an example of physical equilibrium. In this instance, the number of H2O molecules leaving and the number of returning to the liquid phase are equal. So this is the chemical equation for it. Now you see here picture in this liquid water in equilibrium with its vapor in a closed system at room temperature. Liquid water here they are at equilibrium stage. So the study of physical equilibrium actually yields useful information such that equilibrium and vapor pressures are different. So however, chemists are particularly interested in chemical equilibrium process such as reversible reaction involving nitrogen dioxide, dinitrogen tetroxide, nitrogen dioxide to dinitrogen tetroxide, and this is the chemical equation for that another model, that is dimerization takes place when the two nitrogen dioxide molecules combines to form N2O4, and this N2O4 and NO2 gases at equilibrium stage here shown picture, and the reversible process of the reaction can be monitored easily because N2O4 is a colorless gas, whereas NO2 has a dark brown color that makes it sometimes visible in polluted air. Suppose that N2O4 is injected into an evacuator flask here shown like this here flask, and some brown color appears immediately indicating the formation of NO2 molecules. So the color intensifies as the dissociation of this N2O4 continues until eventually equilibrium is reached. Beyond that point, no further change in color is evident because the concentrations of both N2O4 and NO2 remains constant. We can also bring about the equilibrium state by starting with the pure NO2, as some of NO2 molecules combines to form N2O4 and the color fades. Yet another way to create equilibrium state is to start with the mixture of NO2 and N2O4 and monitor the system until the color stops changing. So these studies demonstrate that the proceedings reactions, yes, this is the pictorial representation, general idea here. This is the reversible reaction between N2O4 and NO2. So these two are NO2, this is N2O4. Two NO2 molecules are here, formula. So here what we have observed is nothing but a concentration along y-axis and the time along x-axis. We take the concentration of NO2 is higher in the beginning. That means in this picture, that means change in the concentration of NO2 with the time, the situations here shown. Initially only NO2 is present, suppose the brown color is there. In that case, what will happen? This concentration will be more and it decreases. Once it comes at one point, and that same time the N2O4 concentration also constant to continue. Equilibrium reached. So this entire portion is equilibrium portion. And after that second one, if you observe the concentration on y-axis and time on x-axis, take then initially only N2O4 is present. In that case here, only N2O4 is present and it reaches. This is the point. The entire this shaded spot is N2O4, NO2, constant concentrations are there. And suppose initially NO2 and N2O4 mixture is present, then what will happen in this third graphical representation here shown, it will come like this. Initially N2O4 and NO2 both are there in the mixture. What will happen? This takes time to reach the equilibrium. So in this case, in each case, what will happen? Equilibrium is established to that right of the vertical line. So right of the vertical line means this is the part I have shared here. This is the part. So what they have observed here in this one is nothing but these studies demonstrate that preceding reaction, that is N2O4 to NO2, indeed is reversible reaction, because pure component reacts to give the other gas. The important thing is to keep in mind that equilibrium, the conversions of N2O4 to NO2 and NO2 to N2O4 are still going on. You do not see a color change because the two rates are equal. The removal of NO2 molecules takes place as fast as the production of NO2 molecules, and the N2O4 molecules are formed as quickly as they dissociate. So this is what we have observed in this picture. Now let us see one table form here. This is a table form, and some experimental data of the reaction is just described at 25 degrees Celsius. And the gas concentrations are expressed in molarity, and which can be calculated from the number of moles of gases present initially and at equilibrium, and the volume of the flask in liters. So note that the equilibrium concentrations of N2O4 and NO2 vary depending on the starting concentrations, and we can look for relationship between concentration of N2O4 and concentration of NO2 present at equilibrium by comparing the ratio of their concentrations. The simplest ratio, that is concentration of NO2 by concentration of N2O4, gives scattered values. But we examine other possible mathematical relationships. We find the ratio of NO2 concentration power 2 by N2O4 concentration at equilibrium. So if we take the concentrations of NO2 by N2O4, there are different kinds of answers. But if we do this one as concentration of NO2 power 2 by concentration of N2O4, we'll get a kind of constant values here. So this is the concentrations of N2O4, NO2, initially, these portions, initial portions, and here this is the equilibrium concentrations. So earlier NO2 is not there, but it's that's why its concentration is 0 here, but at equilibrium concentration of NO2 is noticed. Concentration of N2O4 is also noticed, but this is a little bit reduced as it is reactant. Like that, the other cases also came. So nearly the constant value observed in this one is 4.63 10 to the power of minus 3. Regardless of the initial concentrations which are present, that ratio here we called as constant. That constant is we'll call it as equilibrium constant, stoichiometric coefficient. Note that the exponent 2, whatever we have shown over the N2 NO2 in this expression, is the actual same as the stoichiometric coefficient of NO2 in the reversible reactions. We have reversible reaction. What we have shown is N2O4 in equilibrate to NO2. In the stoichiometric coefficient of NO2 is 2. That was shown here. We can generalize this phenomena with this expression, that is AA plus BB gives ratio CC plus DD, where A, B, C, these are actually stoichiometric coefficients for the reacting species, and A, B, C, D are the reacting species. And the reaction at a particular temperature can be written as K is equal to C power C, B power D by A power A, B power B. And as K is called equilibrium constant. And equation here, whatever we have shown, this is formulated by the two Norwegian chemists Cato Guldberg and Peter Wage in 1864, and it is the mathematical expression actually this of their law of mass action, which holds that for a reversible reaction at equilibrium at a constant temperature, the certain ratio of reactant and product concentrations as a constant value. So that constant value is K, that is called as equilibrium constant. For that, all the concentrations may vary as long as given reaction at equilibrium and the temperature does not change. According to the law of mass action, the value of K remains constant as the other values are at constant temperature. And the validity of equation, this 14.2 were shown, this law of mass action has been established by studying many reversible reactions by Goldberg and YRK. And the equilibrium constant then is defined by a coefficient, the numerator of which is obtained by multiplying together the equilibrium concentrations of products and which each raised to the power equal to its stoichiometric coefficient and the balanced equation. And applying the same procedure to the equilibrium concentrations of reactants gives the denominator and the magnitude of equilibrium constant then tells whether the equilibrium reaction favors the products and reactions. Products or reactions. If K is much greater than 1, that means the equilibrium will lie to the right and favors the products. Conversely, if the equilibrium constant is much smaller than 1, then what happens? The equilibrium will lie to the left and the favor of the reactants. So in this context, any other number other than greater than 10 is considered to be much greater than 1. That means any number greater than 10 is considered as be much greater than 1. Then any number less than 0.1 is much less than 1. So although the use of these words reactants and products may seem confusing because the substances serving as reactant in the forward reaction also is a product of the reverse reaction. It is in keeping with convention of referring to substances on the left of the equilibrium arrows as reactants and those in the right as products. So I can see here the reactants, products, whereas equilibrium constant is greater than, extremely greater than 1. Reactants concentration is more here. K is extremely less than 1. It favors the reverse reaction. Okay, that is about regarding the equilibrium discussion. Now we'll see the second point, that is writing equilibrium constant expressions. The concept of equilibrium constant is extremely important in chemistry. As we will see soon, equilibrium constants are key to solving a wide variety of stoichiometric problems involving equilibrium systems. For example, an industrial chemist who wants to maximize the yield of sulfuric acid, say, must have a clear understanding of equilibrium constants for all steps in the process, starting from the oxidation of sulfur and ending to the formation of final product. Okay, a physician specializing in clinical cases of acid-base imbalance needs to know equilibrium constants of weak acids and bases. And knowledge of equilibrium constants of patient gas phase pertinent gas phase reactions will help an atmospheric chemist better understand the process of ozone distribution in the stratosphere. To use equilibrium constants, we must express them in terms of reactants and product concentrations. Our only guide is the law of mass action as shown from Goldberg and YRK, which is the actual general formula of finding equilibrium concentrations. However, because of concentrations of reactants and products can be expressed in different units, and because the reacting species are not always in the same phase, there may be more than one way to express equilibrium constants for the same reaction. To begin with, we will consider reactants in which the reactants and products are in the same phase. The first one thing is homogeneous equilibrium. The term homogeneous equilibrium applies to the reactions in which all reacting species are in the same phase. An example of homogeneous gas phase equilibrium is the dissociation of N2O4, and the equilibrium constant as given in equilibrium equation. We have Kc is equals to NO2 concentration power 2 by N2O4 concentration. Note that the superscript in Kc indicates that the concentrations of reacting species are expressed in molarity or moles per liter. The concentrations of reactants and products in gaseous reactions can also be expressed in terms of their partial pressures. from this equation here, we see the constant temperature and pressure of a gas is directly related to the concentration in moles per liter of gas. As you know, the ideal gas equation, that is P is equal to NOT, where equilibrium process here can be observed for N2O4 and NO2 like this. This in place of concentration, you can write the pressure, that is partial pressure of NO2 and partial pressure of N2O4, where P NO2 and P N2O4 here are equilibrium partial pressures in atmospheres of NO2 and N2O4 respectively. And the subscript of K in Kp tells us the equilibrium concentrations are expressed in terms of pressure. So small p we are showing it that is in terms of pressure. In general, Kc we will write is not equal to Kp because the partial pressures of reactants and products are not equal to their concentrations expressed in moles per liter. A simple relationship between Kp and Kc can be derived as follows. That let's consider the following equation. Here we have AA gives rise to BB, where A, small b are the stoichiometric coefficients, and the equilibrium constant can be written as Kc is equals to B power B, capital B power B by A power A. And an expression for Kp is Pb power B by Pa power A. Anyways, where Pa and Pb are the partial pressures of A and B, assuming ideal gas behavior, the PAV is equal to NART, PA is equal to NART by V, where V is the volume of the container liters. So also we can apply the same thing for the second one, B product, then that can be written as PB is equal to NBRT by V. So that PB and PA values are substituted in the Kp expression. I will get this NB by V power B by NB, NA by V power A, and RT power B minus A will come as a common one. Finally, we will get that relation, that is Kp is equal to Kc into RT power delta N, where the B minus A is number of moles of gases products minus number of moles of gases reactants. Because the pressures are usually expressed in atmospheres, gas constant R is given by 0.0821 late atmosphere per Kelvin per mole, where we can write the relationship between Kp and Kc as Kp is equals to Kc into 0.0821 T power delta N. In general, what happens, Kp is not equals to Kc except the special case where delta N value is 0, as the equilibrium mixture of molecular hydrogen and molecular bromine to give hydrogen bromide, where the delta N value became 0 in that case. In this case, what happens, Kp and Kc both will become equal, as the 0.0821 T power 0 will come, anything power 0 is 1. As another example, we have homogeneous equilibrium. Let us consider the ionization of acetic acid in water, where acetic acid and water, all this is the equilibrium constant. If you write here, concentration of acetate ion into H2O plus ion by concentration of acetic acid into water, this is the equilibrium constant for this one. And we'll use the prime for Kc here distinguished from the final form of equilibrium constant to be derived here. That's why we wrote Kc prime. In 1 liter or 100 grams, 1000 grams of water, there are 1000 grams, 18.2, in other words 55.5 moles of water is there. Therefore, concentration of water is 55.5 molarity, and is the large quantity compared to the concentrations of other species in the solution. Usually 1 molar solution is smaller and compared to this water. So we can assume that it does not change appreciably during the course of the reaction. Thus, we can treat H2O as a constant and rewrite the equilibrium by omitting H2O concentration and the Kc expression. So Kc expression has became equals to CH3CO minus concentration to H3O plus concentration by CH3COH. So now what is this Kc prime is nothing but Kc prime into H2O is nothing but equilibrium constant Kc. So Kc is equals to Kc prime into equilibrium concentration of H2O. Equilibrium constant and its units. Now we'll see equilibrium constant and its units. So note that it's general practice not to include units for equilibrium constant. In thermodynamics, the equilibrium constant is defined as the terms of activities rather than the concentrations. For an ideal system, the activity of a substance is the ratio of its concentration to the standard value, which is 1 molarity. And this procedure eliminates all the units but does not alter the numerical parts of concentrations or pressures. Consequently, what happens, K has no units, and we will extend this practice to acid-base equilibria and solubility equilibria in the next chapters. Example here, we'll have an illustration, that is we'll see discussing about equilibrium constant. See, and this express Kc and Kp if applicable for the following reversible reactions. We have HF plus H2O gives us H3O plus F minus Cl. The second one is 2NO plus O gives us 2NO. Third one is acetic acid with ethyl alcohol forms a sodium ethyl acetate and water. So the strategy here is keep in mind for the first one, the Kp expression applies to only the gaseous reactants. Okay, the second one is the concentration of solvent does not appear in the equilibrium constant expression. So they have given H2O in the equations, first equation. So that won't come in the equilibrium expression. So the first case, what happens, the equilibrium expression, H3O concentration into concentration of F minus by HF concentration. Whereas so the second thing, if you see second equation, that is NO2 is the product, that coefficient is 2. So NO2 power 2 by NO power 2 into O2 is Kc. Whereas that same thing will be applicable for gases products. The partial pressure, if you express then partial pressure of NO2 power 2 by partial pressure of NO whole square into partial pressure of O2. In this, what happens, this Kc for the second equation is expressed like this. Third equation, that is esterification equation. In that case, water can be omitted. Then once we omitted water in the Kc prime, we'll get the equilibrium constant. So the same thing we can write for this one, Kc and Kp for the decomposition of nitrogen pentoxide. Suppose if you write the Kc, that is concentration of NO2 power 4 into concentration of O2 by concentration of N2O4. So N2 5 whole power 2. Whereas of Kp for this X equation can be written as partial pressure of NO2 power 4 into partial pressure of O2 by partial pressure of nitrogen pentoxide power 2. Another example, see the following equilibrium process has been studied at 230 degrees Celsius. They given 2NO plus O2 gives us 2NO2. In this, we have an experiment here. That experiment, if you observe, here concentration of NO given, concentration of O2 given, concentration of NO2 given. So that is substituted, I got 6.4 to the power of 5 came from the calculation. It indicates that when they have supplied the equilibrium concentrations, we can find the equilibrium constant easily from the expression, that is NO2 power 2 by NO power 2 into O2. The same way, they have asked us to do something here like this, that is CO plus Cl2 gives us COCl2. CO concentration given, Cl2 concentration given, COCl2 concentration given. So what is Kc? First we'll write the expression, that is COCl2 concentration by CO concentration into Cl2 concentration. So COCl2 given 0.14 divided by concentration of CO given 1.2 into 10 power minus 2, and Cl2 concentration is given as 0.054. So you can simplify and get the answer. Right. Next. Equilibrium constant for the decomposition of phosphorus pentachloride to phosphorus trichloride and molecular chloride is found to be 1.05 at 250 degrees Celsius. Means the Kp value they given in this question. At the equilibrium partial pressures of PCl5 and PCl3 given respectively. Then what is the equilibrium partial pressure of Cl2? So first, when you write the equilibrium concentration with respect to partial pressures, from that you can find what is the partial pressure of Cl2. That is Kp into partial pressure of PCl5, partial pressure of PCl5, that is PCl5 divided by partial pressure of PCl3. So the substitute here, the value got 1.98 atmospheres. Okay, let us move to the next one. That is another practice question given. You can also check it. So in this question, they are given partial pressure of NO2, partial pressure of NO, but O2 partial pressure they have asked us to calculate. So what is partial pressure of O2 is nothing but Kp value given 158 here. That is Kp into that is partial pressure of NO2 power 2 divided by partial pressure of NO power 2. So in this, we have to substitute these values. Kp value is 158 into partial pressure of NO2 given is 0.400 whole square by partial pressure of NO given 0.270 whole square. Let us go for simplification and finalize it. Next. Methanol is manufactured industrially by the reaction. This is reaction CO plus 2H2O. 2H2 gives us CH3OH. The equilibrium constant Kc for the reaction is given as 10.5 to 220 degrees Celsius. And what is the value of Kp at this temperature? And the relationship between Kc and Kp is given. Kp is equal to Kc into delta power T power delta n, where R value is 0.0821. If you take, then from this reaction delta n value is 1 minus 3, that is minus 2 will come. So that will be substituted, and R value and Kp value already they given. Kc value is 10.5. After substitution, you get 6.4 to the power of minus 3. Likewise, you can also find Kc for this practice exercise. That is Kc, they are asking us to find what is the relation between Kp, Kc is Kp is equals to Kc into 0.0821 whole power delta n. Whereas if they ask Kc, then it will become Kp into 0.0821 whole power minus delta n. So in this, we have to substitute the Kp value given the question is 4.3 into 10 to the power of minus 4 into 0.0821 whole power. Delta n for this reaction, delta n for ammonia formation reaction is 2 minus 4, that is minus 2, that we will write minus 2. So we will simplify to get the answer. This is the main part of this discussion. Likewise, when you see the heterogeneous equilibria, as we might expect, one thing that is heterogeneous equilibria results from reversible reaction involving reactants and products that are at different phases. Example, when a calcium carbonate is heated in a closed vessel, the following equilibrium can be established. That is, the CaCO3 gives us CO plus CO2. Thus, two solids in one gaseous constant is there in the separate phases. At equilibrium, we might write the equilibrium constant like CO and CO2 by CaCO3. Whereas the concentration of solid, like its density and its is an actually intensive property, does not depend upon how much the substance is present. So, for example, molar concentration of copper is there, 8.96 grams per centimeter cube is at 20 degrees Celsius is same whether we have 1 gram or 1 ton of the metal is there. So that's why this is irrespective of this physical state concentrations of these things, we will omit in the expression. So for this reason only, the terms of concentration of CaCO3 and CO themselves constants, and that can be combined with the equilibrium constant. So you can simplify this above Kc prime into Kc is equal to CO2 concentration. So where Kc is a new equilibrium constant conveniently expressed in terms of single concentration that of CO. Note that the value of Kc does not depend upon how much CaCO3 and CO are present, as long as some of each is present at equilibrium. See, CaCO3 and CO, they are gases, solid state. So solids don't have any kind of impact on pressure. So equilibrium with respect to partial pressures cannot be expressed with the solids and liquids. The situation becomes simpler if we replace the concentrations of activities in thermodynamics. The activity of the pure solid is 1, thus the concentration in terms of CaCO3 and CO are both in unity on the preceding equations, and we can immediately write the Kc is equal to CO. Similarly, Kc value can be written like this very simply, because the activity of pure liquid is also 1 like the solids. As a reactant or a product is liquid, we can omit it in the equilibrium expression. So here CaCO3 is a solid, CaO is a solid, whereas CO2 is a gas. So we can express this equilibrium constant finally as Kp is equal to P partial pressure of CO2. So equilibrium constant in this case numerically equals to the concentration of CO2, partial pressure of CO2, and is easily measurable quantity. We'll see an example here. Write the equilibrium constant expression Kc and Kp if applicable for each of the following heterogeneous systems. So the first expression, if you see H2SE, hydrogen selenide is a gas, ammonia is a gas, where it says ammonium selenide is a solid. So for that case, we will omit NH for twice Se, and we'll consider it as unity, and we'll write Kc as NH3 concentration power 2 by H2Se concentration. Similarly, in place of the concentration, we express the partial pressures for Kp. You can write Kp is equal to partial pressure of NH3 into partial pressure of H2Se. NH3 power 2 will come here. On the second question, if you see AgCl, second expression, if you see, we have, this is the second expression. First expression is got over. For the second expression, AgCl given as a solid, so the equilibrium constant can be written as Ag plus concentration into Cl minus concentration. Whereas third one, if you see, you can P4 is a solid that is combines with Cl2 gives PCl3, and PCl3 is a liquid, P4 is solid. Finally, you'll get Kc as 1 by Cl2 power 6, because P4 is solid and PCl3 is liquid. They do not appear in the equilibrium constant expression. Thus, Kc is given as 1 by Cl2 concentration power 6. Alternatively, what will happen is we can express the equilibrium constant in terms of pressure as 1 by partial pressure of Cl2 power 6. Another thing here, write the equilibrium constant expression Kc and Kp for the formation of nickel tetracarbonyl, which is used to separate the nickel from other impurities. So in this case, what will happen is nickel is solid and remaining are gases. So if you write the Kc will become equals to NiCO4 concentration divided by CO concentration power 4. Alternatively, Kp can be written as Kp is equals to partial pressure of nickel carbonyl NiCO4 by partial pressure of CO power 4. Another question here, consider the following heterogeneous equilibrium CaCO3 gases CO plus CO2. At 800 degrees Celsius, CO constant pressure, CO pressure is given as 0.236. And they're asking us to calculate Kp and Kc for the reaction at this temperature. For example, if you find the Kp value like is given here, partial pressure of CO2 given in the question, which become equals to the Kp value as concentration of CaCO3 and the concentration of CO become unity. Partial pressure of CO2 given in the question is 0.236. That's why we got 0.236. And keeping in mind that relation between Kp and Kc, so you can find Kc is equals to Kp into RT value, R value 0.0821 whole power minus delta N. So Kp value in the question given we have obtained is 0.236, 0.236. 236 into 0.0821 whole power delta n value is 1. So that is simplified value get 2.68 into the power of 4 minus 3 got. Another practice question here given, you can take it down. So here also the same thing will be repeated. But here first we have to find the Kp value. That value is partial pressure of NH3 into partial pressure of H2S will come. Then after we will find Kp value, Kc value by putting the Kp value in this Kc expression. That's Kc is equals to Kp into RT power delta minus delta N. So this is what we discussed, and we'll continue this one in the next session. Until